Hello everyone, welcome to DataFuse Analytics. In the previous video, we learned about generative AI model families. Today, we will be learning everything about an interesting and important generative AI topic which is called as autoencoders. Autoencoders are a type of approximate density functions. So let's learn autoencoders today. So in this video, we will explore architecture of autoencoder, learn how to design and train autoencoder right from scratch using Keras. We will unlock autoencoder's creative potential in generating new images, and also we will examine their limitations, reminding us that even in the world of AI, there are boundaries to explore. Let's get to know the basics of autoencoder. An autoencoder is simply a neural network that is trained to perform the task of encoding and decoding a particular item. Now this output from an autoencoder should be as close to the original item as possible. Now let me explain you these 2 points with the help of an architecture diagram of an autoencoder. So this is the entire architecture diagram of autoencoder. Now autoencoder is mainly made up of 2 components which you can see on the screen. The first important component is encoder and second important component is decoder. An encoder network compresses high dimensional input data such as image into a lower dimensional embedding vector, or we call it as a context vector, or even some people call it as hidden representation. This vector is represented as Z in this diagram. A decoder network decompresses this embedding or this context vector back to this original domain. Now you might have observed that output image is slightly blurred. Now this is to depict the loss of information during encoding and decoding. Well, it also depends upon the dimensionality of context vector. Higher the dimensionality of context vector, less will be the loss. Lower the dimensionality of context vector, higher will be the loss. This loss is about the reconstruction loss I am talking about. Now this context vector or embedding vector or this Z is an interesting component, or it is an interesting part. Now remember this, the concept is that if you pick up a spot or a point in the latent space or hidden space, we can create new images by running this point through the decoder. Now this works because the decoder has learned how to turn points in the latent space into usable images. Now in order to implement it, let's design our encoder-decoder architecture. The input image that we will be dealing with while implementation will be of resolution 32x32. It will have one channel because it will be black and white images. This encoder will consist of 3 convolutional layers, and we will be using a stride of 2 to halve the size of output each layer. Now this decoder is the mirror image of this encoder. Instead of convolutional layers, we will use convolutional transpose layers. And finally, the output image that we will be getting from this encoder-decoder architecture or from this autoencoder would be 32x32. The resolution will be 32x32. Now let's start with implementation of this encoder-decoder architecture. Let's start implementation of autoencoders in Python. I will be using Google Colab to implement this. Before implementation, I will set my runtime to some GPU. So T4 GPU is available. Okay, so for this implementation, we will be using Fashion MNIST dataset. Now this dataset is a collection of grayscale images of clothing items, and each image is of size 28x28. Let's start this implementation by importing few libraries which we require. So first library that we require is NumPy. So import NumPy as np. Second library we require to display images or to plot images. Import matplotlib. Then we require TensorFlow Keras. So these are all the libraries which we require for today's implementation of autoencoders. The first step is data preparation. This dataset which we discussed, this Fashion MNIST dataset, comes pre-packaged with TensorFlow. So it can be downloaded by using this line. So xtrain, ytrain, then test data x test y test equal to, we will use the datasets module, datasets dot fashion mnist dot load underscore data, and we will run this block of code. Now these images contained in this dataset are originally 28 cross 28 in grayscale with pixel values ranging from 0 to 255. To make these images suitable for our neural network, we will pre-process them by scaling the pixel values between 0 and 1. Additionally, we will pad the images to a size of 32 cross 32 to simplify how we work with the data as it goes through the network during forward pass and so on. So let's write a pre-processing function. Pre-process images, and here we will input images as argument. So images is equal to images.as type load 32, and we will divide it by 255 so that they will scale between the values 0 and 1. Then images is equal to, we will pad these images so that the size of the image becomes 32 cross 32. Images 0, 0, then 2, 2, then 2, 2, and constant values equal to 0.0. Then images is equal to np.expand dimensions, we will give images comma -1, and then we will return images. Okay, let's pre-process xtrain and xtrain and xtest. We will call this function pre-process images, and we will give input as xtrain. Again, for pre-processing xtest, we will call this function and we will give xtest. Let's run this block of code. Okay, now that our input images are pre-processed successfully, now we will write few helper functions to display images, because we want to visualize what is exactly going in our neural network, and we have to analyze our data as well. So we will require few helper functions to display images. Now one tip to all of you guys, you can simply copy paste these two helper functions from the notebook, which I have pinned it in the description box from my GitHub repository. But I'll write it for you from scratch. Let's say sample batch. We will give dataset and batch equal to dataset dot take get single element. I'll not describe this code because this is out of scope for this particular session, as we have to learn autoencoders. So if you have any doubt in this particular code, please ask me in the comment section and we can solve it together. We will simply return this batch, but in NumPy. Okay, now the actual real function of display images. Input will be images, then number of images to display number of images to display, we will set it as 10 as a default. Then size would be, let's say, 20 cross 3. Then CMap, we will select CMap as, let's say, gray underscore R. Then type would be float 32, and we don't have to save it anywhere, so save to equal to none. So these are the input keyword arguments. Now let's write the actual function in display images. Images.max greater than 1.0, then images equal to images divided by 255.0. Dot min is less than 0.0, then images equal to images plus 1.0 and then divided by 2.0. Then we will call plt dot figure, and we will require figure size to size. Then we will write a for loop. So for I in range this number of images to display, let's take x1 equal to plt dot subplot 1 comma number of images to display, and then number of images, that is I plus 1. Then plt dot im show images of I dot s type. We have already decided our type as this float. We'll just type it here, and then CMap equal to CMap. Let's set plt dot axis equal to plt dot axis is off. And then plt dot show. We want to be requiring this save to keyword for now. Let's run this. Now let's display this few images from training dataset. So we will call this display images, and we will simply pass xtrain here. Let's see how our function works. It should display 10 images because we have set 10 as default number. So these are the images which are present in the training dataset. Also we can display images in our test dataset. We just have to simply replace this with x underscore text. So these are the images from test dataset. Now let's design our autoencoder. Let's design autoencoder. So as we have discussed during the presentation, we will design autoencoder in similar manner. But before that, we have to list down few parameters. So image size equal to 32. Okay, we have channels as 1. We will set epochs. Training epochs will be, let's say, 5. Embedding dimensionality, that is the dimensionality of the hidden vector or context vector. We will set it 2 for now, just to visualize in 2 dimensions. So we will set batch size as 100, let's say. and then we will have buffer size as 1000, then validation split as 0.2. I think that's it for parameters. If we want to declare more parameters for training, we can go to this block of code and we can edit this block of code. Now let's code for actual encoder. First is we need to define input layer. So encoder, let's define input layer of encoder. So let's say encoder input equal to, we will use the Keras layers and we will simply use dot input, and we will give shape as this image size, and number of channels. We will give a name to this layer. Let's give name as encoder input. Let's say layer. Then we will define stack of convolutional layers. So we will define 3 convolutional layers. These convolutional layers will be on top of each other. So let's say x equal to layers dot con 2d functionality from layers of Keras. The input would be 32, 3 cross 3. Strides would be 2, and we will set activation as relief, rectified linear unit, and padding would be same. So if you want, I can make a separate video on convolutional neural network if you want to understand what is stride, what is padding equal to, same, means, and so on. Please write in the comment section whether you want this type of video or not, and we will give this as encoder input. Okay, we will connect this layer to encoder input. Then we will get another layer of convolutional 2D. I'll just copy paste it so that I don't have to write again and again, and I'll just change these values. So instead of 32, I'll write 64, and everything will be same except here we will give the preceding layer, that is x. Okay, then the third convolutional layer, again I'll copy paste. Instead of 64, we will write here 128, and everything will be same including this x. So that's it. Now we will flatten the output. Flatten the output from this last convolutional layer. So flatten the output from last convolutional layer to a vector. So this will be a vector. So we will take a variable, that is shape, before flatten equal to k dot int underscore shape. We'll pass it as x. Now this will be required in future by decoder layer, by decoder block. So keep this in mind. So then we will flatten layers dot flatten. We will pass it the last convolutional layer. Okay, now after flattening we will design a dense layer which will connect this flattened vector to let's say 2D embeddings or context vector. So encoder output equal to layers dot dense, and then we have to pass the embedding dimensions. So embedding embedding dimension, which we have already specified here, this embedding dimension, and we will name this layer as encoder output layer, and we will pass X to this particular encoder output layer. Now the Keras model, which defines now we will have encoder variable, then models, we will pass encoder input and encoder output. Now let's print model summary, or let's print this encoder model summary. Encoder dot summary. Let's run this block of code. Okay, we are getting an error, invalid syntax. Maybe you want, okay, let's solve this particular error. The error is in this line, layers dot input shape equal to image size comma channels. Oh, okay, so this will be the shape. Okay, and then we have to name, so name equal to encoder is a part of this layers dot input argument. Let's run. Okay, again an error in next line. I don't think this is necessary. Okay, now it is running. Okay, we got another error. X equal to layers dot flatten X, required in future by decoder. Okay, module, this has no attribute flatten. Let's solve this code. Sorry, let's solve this error. I think it should be written in capital, layers dot flatten, and again we got another error, that is it has no attributes model. It should be model. Okay, now that we have solved all the errors, this is the architecture of encoder. So this architecture is similar to what I represented it with the help of a diagram. This is the layer type, encoder input, convolutional, flatten layer, and the output layer. Here you can see the total number of parameter, total number of trainable parameter and non-trainable parameter. And if you want to see how many number of parameters are there in each layer, then you can see it here. Okay, now let's code and design for decoder. Let's define input layer for decoder. So decoder input will be equal to layers dot input, shape will be 2 cross 2, that is 2 cross, and we will give a name to this decoder layer. Let's say decoder input layer. So similar type of coding we will do for decoder, but this decoder will be a mirror image of encoder. Now we will connect input to dense layer. So here we will define X and layers dot dense, np dot prod. Now we will use this shape before flatten. So here I have already told you, like we require this variable required in future by decoder. So we will require this now when actually designing and implementing this decoder. And then we will input here decoder input. Okay, now we will reshape. Now we will reshape this particular vector which we will get from this layer into a tensor that can be fed as input to the first convolutional transpose layer. So reshaping to feed as input to first convolutional 2D transpose layer. So we will use layers dot reshape, and we will again use this shape before flatten variable and then x as input. Now let's design a stack of convolutional 2D transpose layers, and these layers will be on top of each other. Okay, so here x is equal to layers dot conv 2D transpose. First will be 128 dimensions and then 3 cross 3, and then strides will be equal to 2. We will set activation as rectified linear unit. We will set padding equal to same. So again I am repeating, if you want to know what is this 128, 3 cross 3, strides, activation, padding in convolutional neural network, please write a comment whether I should make a separate video on that or not. Then we will pass this x. Okay, this is the first convolutional transpose layer. In order to code the second this convolutional transpose layer, I'll just copy paste it, and instead of 128 we will have 64 here, and everything will be same. Now we will define third convolutional layer. I'll just paste, and instead of 64 here we will have 32. Now we will have the decoder output layer. So decoder output equal to layers dot conv 2D. Here it will be 1 cross 3 comma 3. Strides will be equal to 1. Activation will be equal to sigmoid. Padding will be equal to same, and name of this layer will be decoder output layer, and we will pass x to this particular layer. Okay, now decoder equal to models dot model, similar thing which we done while designing and implementing encoder. So models dot model decoder input and decoder output. Then we will simply print summary of decoder. Let's run this. Okay, so without any error we have executed this. Again you can see for each layer you can have number of parameters, and for decoder the total trainable parameters are this, and non-trainable are 0. Okay, so about 2,46,273 parameters are trainable parameters for our decoder. Now the most important part is joining this encoder to this decoder. Let's join it. So let's join encoder to decoder. Let's define this as our autoencoder. So autoencoder equal to models.model encoder input comma decoder, and here we will select encoder. Here we will give encoder output to this decoder. Then we will simply print the summary of entire architecture, autoencoder dot summary. Encoder output is not defined. Okay, so here is the encoder output. Okay, I have made a spelling mistake here. Okay, so this is the total architecture of encoder plus decoder. So the total number of trainable parameters are now roughly about 3,43,000. Now, why to wait? Let's train this model. So, training our autoencoder. Before training, we have to compile this entire autoencoder architecture which we designed it. Now in order to compile, we have to give two arguments. First is optimizer and second is loss. So let's compile autoencoder dot compile optimizer equal to Adam optimizer, and then we will select loss as binary cross entropy. We can use RMSE loss as well, but this means that the generated output will be symmetrically distributed around the average pixel values. But on the other hand, when we use this binary cross entropy, the loss is asymmetrical, and thus it penalizes error towards extreme more heavily than error towards the center. So that is why we will be using this binary cross entropy loss. Let's compile this model. Now we have to save this model, right, somewhere. So let's create a model checkpoint variable, and then we will use callbacks functionality. In this we have to give file path. So I'll simply give file path as my current directory. It will automatically make a folder which is named as checkpoint in my current working directory. And I'll tell him to save weights only as false because we want everything to be saved. And save frequency would be based on epoch and not on steps. We will set monitor as loss, mode will be equal to minimum, and let's also give this argument, that is save based only, as true in order to save memory, and let's set verbose as 0. Okay, then we will use this tensor board so we can visualize training loss, validation loss, and etc. Equal to callbacks dot tensor board, and we will set logging directory as let's say tensor board logs. Let's run this. Okay, now let's actually train the model. So we will use the fit functionality, encoder dot fit. So in traditional machine learning algorithms also we use fit functionality when we use scikit-learn package and all. So here this is same, like first we have to give the training data, X train and Y train. Then we will set up epochs, and then we have batch size, then we will let shuffle as true, and then validation data equal to X test and Y test, and finally callbacks will be this model checkpoint and TensorFlow callback. So here TensorFlow callback. Let's train this model. Oh, the name Auto-encoder. My mistake. So here we are encountering an error. Logits and labels must have same shape, but received 132 versus 100. So here the input and output would be the same because we are trying to reconstruct images. Okay, now the code is running. So this is the first epoch, which is taking about 10 seconds to run. Here validation data will be again X test and X test. We are not predicting anything, right? We are just trying to reconstruct the original image with minimal reconstruction loss. So keep this in mind. We are not classifying images into n number of labels as we traditionally do. We can see that the loss is slowly reducing from 0.2675 to 0.2525 validation loss, and the training loss started at 0.3, and after the end of fifth epoch the loss is 0.2517. We can give it for more epochs to train. The loss is decreasing, but this is just a prototype method or prototype approach or a prototype model, we can say, and that's why we will just train it for 5 epochs. Now let's save these particular models, save the checkpoints or trained model. We will use Autoencoder dot save. We will save this in models directory in this Autoencoder. Then if you want to individually save this encoder, then you can also save. We will require this individual encoder and decoder when we actually have to regenerate new images and to see how encoder is storing this hidden representation or context vector. So that's why we are saving this encoder and decoder separately as well. And then decoder dot save in models directly and then decoder. So if you are using Google Colab, it will be stored in your current working directory in this models folder. In encoder, all the encoder files will be saved. In decoder, all the decoder file will be saved, and in encoder all these encoder file will be saved. So we have saved our autoencoder, entire encoder decoder, then we have decoder and encoder. Now we have trained our model, we have also saved our model. Now let's actually reconstruct images. So that was the whole point, right? Like reconstruct images using our trained autoencoder. I'll close this particular tab. Let's write the code to reconstruct images. So let's say we want number of images as 1000. Then example images, we can take it directly from our testing data and from our training data. Here we will use this variable. Similarly, so example images we have got, and then just to visualize the labels, we can use these labels, y test and then images. So we have selected first 1000 images from this testing dataset, test dataset. So let's say predicted images as Auto-encoder. We will simply use predict functionality, predict, and we will input this entire example images. So it will predict for this first 1000 test images. Let's run this. It is pretty fast, right? Within 1 second it predicted for 1000 images. But we have to also remember that the images are of only 32 cross 32 pixels. So they are not huge images as we currently have in our mobiles, like 4K image or 24 megapixel, 4800 megapixel images and so on. Let's display our predicted images. So we will use this display methodology which we already wrote before, this display images. We will call this functionality. So this is a very handy helper function. Predicted images. So it will it will display the first 10 images. If I want to display 20 images, then I'll just set this number of image to display as 20, and it will display first 20 test images which it predicted. So these are the images that it predicted. So predicted in the sense reconstructed images or generated images. Now the next part is visualizing embeddings or the latent space, how it represented image in the context vector, that is Z, which we already saw during our presentation. So let's write the code for that. So visualize embeddings or context vector. Let's not call it as context vector, let's call it as latent space. So here embeddings equal to, we will use this encoder and we will predict all of the example images. Let's give this example images as a bigger number, let's say 5000. So that we will have more data to visualize our latent space. So it only took few seconds to predict this particular image from this encoder. Okay, so now we have constructed embeddings for each and every image. Let's print embeddings for, let's say, first few images. Embeddings, let's say first image. So this first image is represented by this two-dimensional vector. Okay, now this 32 cross 32 pixel image is represented by these two numbers. Imagine the compression that we have achieved. So we don't have to store the entire image, we just have to store one model and this particular representation of image. So it really helps in image compression. So many methods are related to this. Like you just have to store these embeddings, and with these embeddings or latent space you can reconstruct an image from these two numbers itself by using decoder. Imagine if you want to print, let's say, embeddings of this 10 images. Now this is a very cool approach, right guys? Just by using this two image, I am representing my first image, and just by using these two numbers I am representing the 10th image in a dataset. These numbers or this vector or this hidden dimension or this hidden latent space might not be understandable to us, but this is pretty much understandable by the decoder of the trained model of your system. Now let's plot all these points. Okay, I'll again write a few lines of code to plot this. So let's define the figure size. Why not keep it as, let's say, 12. Then plt dot figure fig size equal to, let's give it as 12 cross 12. And then let's print a scatter plot of embeddings. And we need to have x and y axis, and that's why we are writing like this. We will set C as black and white, that is black, and alpha as 0.5. Let's select SST 3, sorry, plt dot show. It got an unexpected. Okay, let's solve this error. This hyphen should not be there in this argument. So this is how. Let's decrease the size of this. Let's say 8. So we can read it in one entire screen. Okay, now this is visible. Okay, so this is each dot represents an image. So this dot is an image, this dot is an image, this dot is an image, but they are now compressed in a 2D representation. So if we want to plot this, we just have to pick this point, give this point to decoder, and decoder will regenerate image. Now we can take any point here in this entire box. Now guys, here suppose this is my cursor, right? I can click here, I can take this point and I will give it to decoder. Decoder will generate anything. It will try to generate something. Okay, whether it might be meaningful or it might not be meaningful, that we will be seeing in this session. That we will be seeing in some time, whether it generates meaningful or not. But this is a simple black and white graph, right? We don't know what are label IDs. We don't know what is, let's say, shirt or this pant and so on. We don't know what it is. Now let's color this particular embeddings by their clothing type. So we have total 10 labels in this MNIST dataset, fashion MNIST dataset. Let's color these embeddings so that we can represent it in a more meaningful way. But you got right, you all got what these points mean and so on. Let's color these embeddings. Color the embeddings. As per label IDs. So example labels equal to y underscore test, and then we have got a number of images, this number of images. Okay, so we have example images and example labels. Then we will set as figure size. We already said that. Then plt dot figure fixed size equal to let's copy that particular variable fig underscore size 8 cross 8 so that it can be visible without zooming in or out. Then again plt dot scatter. The same thing we will do, like embeddings 0, this one for x and y axis. Then we have cmap equal to rainbow. So each and every ID will be represented with different shades of a rainbow. Then c equal to example labels. We will again set alpha is 0.5 and ss3 plt dot we will also have a color bar just to get an idea about what color represents what ID, and then plt dot show. Tada! Come on. This is a very interesting and cool diagram, guys. So here this green part is of ID 4. This is a different type of clothing. This violet, this orange and red are different type of embeddings and so on. So in this way the features in hidden dimensionality are represented by this encoder. But here we can observe few things, like some clothing items, let's say these items, they are represented over a very large area, right? And few items, let's take these items, they are clustered in a very small area. So this is one limitation of this autoencoder. Few items cover very huge area and few items cover very small area. Now the distribution is again not symmetrical about the point 0 cross 0. So this is my point 0, right? Most of the distribution is in the negative side. Some of the points are lying towards positive side, right? And also we can see that this huge piece of chunk here, this white gap is there. Again this white gap is there. So encoder don't know whether so encoder doesn't have any idea about this white patches, these patches which we have. There are these patches are very huge. So if I select a point from this patch, which we will do in the coming minutes, the encoder will confuse which clothing item it has to generate. But suppose if I select a point from this orange, okay, this orange is of ID 9, right? 8 and 9. So this red and orange, it will generate this particular label IDs, but it will fail to generate a point if I take a point from this white patch, or we call it as holes. Okay, so this is a very cool graph that we have plotted, a very cool scatter plot. So we can actually so I am excited here now, because we have actually compressed this image. After compressing, we have plotted all this dimensionality, that is hidden latent space, and we have gotten to know what is exactly going in the back end of this encoder, right? Now let's try to generate new images from decoder. We will not generate a test image, we will generate altogetherly new images. Now in order to generate new images, we just have to select random points from this box. From this box, entire box, you can just select random points, let's say here, 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 here. It can be between this colored embeddings, or it can be outside these embeddings. But we have to get the range of the existing embeddings and so on, that we will be coding in this, and then pass this two-dimensional vector to decoder. Decoder will generate superb images. Okay, so be with me. Now let's come to the most interesting part of this video. Like let's try to generate new images. Let's force our autoencoder, our trained autoencoder, to be more creative in generating images. Okay, now we can generate images within this bounding box, of this hidden representation like latent space. So we have to define boundaries. So mins and max equal to np dot minimum of what? This embeddings, and axis 0. Then np dot max again embeddings, axis as 0. Then we have to select something called as grid width and grid height. Actually, I'm like more excited to generate new images. I wanted to see how these images are getting generated and what these images looks like. Then sample equal to np dot random, let's say random dot uniform, and here we will input mins, max, and size equal to this grid width and height. And here we will write embedding dimensionality. Let's run this. Let's solve this error. Okay, here np dot min, it has to be closed, and then np dot max. Okay, let's decode the sample, let's say points. So reconstructed images equal to, we will use decoder dot predict and let's say sample. Okay, before that let's print this sample, right? So these are the sample images, first image, second image, first random point which we took from that particular bounding box, this latent space, and so on. So we are doing like this. So for each and every two-dimensional vector, an image will be generated by this decoder. Let's display these images, right? These reconstructed images. So display images and then reconstructed images. Let's run this. Okay, so this is the images which are actually generated by decoder. How cool is this stuff, right? These are actually the new images that we are forcing decoder to generate, but still it is not a clear image and so on. But see this one, this doesn't look anywhere to the clothing thing, and also this one. Okay, if we make it more clear, then this can be a trouser, but right now it is just a rectangular box. Now we will see why this is happening. In order to see this, we need to check which points, this sample points, it's selected from this image. We need to plot this point on top of that particular hidden space. Let's plot this. Now we are trying to reason why we are getting this kind of output. Now this is a good image, footwear image, and this is also a good image, a trouser image, but this kind of images is not what expected from an autoencoder, right? These meaningless images. Let's plot this. Let's say my figure size we already specified. then plt dot figure fig size equal to fig underscore size comma fig underscore size, which we already defined this fig size. Then we will again write a scatter plot. What I'll do is I'll straight away take this code and I will paste it here. Okay, now we will also plot the newly generated points. This newly generated points is this sample. So plt dot scatter, then again we will call it for a y-axis 1, let's say c equal to let's give it a color. Okay, let's copy this and paste it here. Hash, and alpha will be 1. Let's set as s is equal to 2. Okay, let's set s as 40. Then we'll show this. Let's run. So these are the points. See, these are the points which is randomly sampled, and most of the points are lying on this white patches. See this point 1, 2, 3, 4. These are the points which are lying in the white patches, and that's why we are getting this type of unmeaningful images or meaningless images. But the points which are generated from this cluster, like this 4 points, and these 2 points, they are actually they will be meaningful, right? But the points which are generated from these white patches, and the decoder will try to generate something, but it will not be meaningful. So let's try to improve this particular graph by adding a grid of decoded images as well to it. So let's code. H space we will give it 0.5, let's say, and W space we will also give 0.5. Then we will write for each image, for I in range, grid width into grid height, which we already defined it earlier. Then AX equal to fig dot add subplot grid height, grid width, and I plus 1. AS dot axis we will set it as off, and AS dot text we need to add text like from which point that particular image is generated. So we'll write here then we will define font size as, let's say, 8. Then it will be center alignment and transform equal to as dot trans axis ax dot im show reconstructed images. We will just copy paste this variable name. Just sorry for this particular misspelling. Okay. Reconstructed images I, comma, and then cmap equal to gray. Let's run this. Hopefully it won't give any error. Oh, we have got it. So here we can see that this particular sample 9.9 and minus 3.4, it gave us this particular image of trouser. This minus 6.4 minus 8.5 give this image of a sandal. So in this way you can actually generate images or generate new images from your decoder. Some images which are falling on this white patch might be senseless or meaningless, but the images which are sampled or the points which are sampled from this cluster that will be more meaningful. Now we will see the limitations of this autoencoder. Now that we have completed implementation of autoencoders, let's understand the limitation of autoencoders. So there are three important and three major limitations of autoencoders. The first limitation is, we can see that if we pick points uniformly in a bounded space that we define, we are more likely to sample something that decodes to look like a bag, that is ID 8, than an ankle boot, that is ID 9. Now because the part of the latent space carved out for bags is larger than the ankle boot area. So this bags is represented by orange point and ankle boot area is represented by red points. The second major limitation is, it is not obvious how we should go about choosing a random point in the latent space, since the distribution of these points is undefined. And the third important major limitation of autoencoders is, we can observe that there are gaps in the latent space where none of the images are represented. The autoencoder doesn't prioritize making in these regions correspond to recognizable clothing items because very few training set images are encoded in these gaps or in this space. So that's it guys for this autoencoders video. Hope you all got something to learn about autoencoders. If you have any doubt, please comment in this comment section. If you have watched video till now, like this video and subscribe to the channel. Your subscription supports me a lot. Thank you guys.